All right, let's get going. So we're very happy this week to have Aida Maraj talking. She's from Michigan, and she's going to tell us about asymptotic behaviors of hierarchical models. So go ahead.
So first, thank you to Andrew and Jenny for inviting me to speak at this seminar. So this talk will be about the representation stability appearing in some algebraic objects motivated by statistics. So the work presented here is based on joint work with my PhD advisor, Uwe Nagel. Okay. Somebody has the speakers on. Okay, so the storyline of this talk will be as follows. I will start introducing these hierarchical models and their ideals. Then when I will present ideals, we will see that one can very naturally associate to them a group action by a product of symmetric groups. And that's what we will do next. And with respect to these symmetric groups, we will create filtrations of such ideals. And in the third part, we will take advantage of the fact that we are dealing with infinitely many objects that are very similar to each other and draw some conclusions on asymptotic behaviors of these models, including qualitative and quantitative properties of these models. Okay, so let's start with the first part. So hierarchical models are discrete statistical models. This means that they are sets of points, subsets of points of the probability simplex. In other words, like they are points in some Rm such that each coordinate is non-negative and the sum of all the coordinates is 1. They are used in data analysis, and they are a collection of probability distributions that record the dependency relationships among random variables for given data. Luckily for us, they can be visualized. So they are realized by simplicial complexes with positive integers associated to each vertex. Here is one such example. So we see we have a simplicial complex with 4 vertices. Each vertex, this means that we are dealing with, in data, we are dealing with data that is classified according to 4 random variables. Each vertex it represents 1 random variable, and the positive integer that we associate to that vertex is the number of states or the number of options that that random variable has. And we have that some vertices are in the same phase of the simplicial complex, if and only if the corresponding random variables are not independent on each other in statistics. Throughout this talk, I will denote a simplicial complex by delta, and I will call a simplicial complex by giving its maximal faces, so by giving its facets. For instance, in this case, I have 2 facets. I have the facet 1, 2, 3, and 3, 4. Also, this I will record this number of states in one vector, which I will call R, and I will often call this vector R as the vector of states. Now, by the way, I forgot to say, so if you have any questions, please, you are highly encouraged to interrupt me and ask the question. The most famous hierarchical model is the independence model. And so this is the model that says that all the random variables are independent on each other. Visually, this is represented by a simplicial complex that is just a disjoint union of vertices, as the one here. Throughout this talk, we will also consider like a generalization of these independence models, which will be just a disjoint union of simplices, like the one here. And soon, when we go to the algebra, we will notice that the most important hierarchical models will correspond to some of the most important objects in algebraic geometry. Okay, so I promised that there is an ideal associated to a hierarchical model. Now, in order to avoid heavy notation, I'm presenting this recipe via this example. So in this case, delta has facets 1, 2, and 1, 3. And let's take, for simplicity, that our vector of states is 3, 2, 3, 3, 2, which means R1 is 3, R2 is 3, and R3 is 2. So what we will do next is, with this information, we will form two polynomial rings. And then we will form a monomial map. We will define a monomial map between the two polynomial rings, and the kernel of that monomial map will be the ideal associated, or the ideal of the hierarchical model for this delta and R. Okay, so let's explain step by step, like the parts. So we said that we form first two polynomial rings. So the source ring will have variables that are indexed by the state space. So this means like 1, 1, 1 till 2 in this case, R1, R2, R3. And notice that this is the first ring is just using the vector of states R. Now the second ring uses the information from delta. In particular, every facet in delta induces a collection of variables. So the facet 1, 2 will induce y1, 1 till to y r1, r2. Similarly, the facet 1, 3 will induce z1, 1 till to z r1, r. Did I say r3 here? Sorry, I meant r2. r1, r2, and here r1, r3. And the monomial map will send each variable xij to the product yij times zik. So notice what's happening with this monomial map. So the vector of indices ijk is being projected down twice, one time to the first and to the second coordinate ij, which is exactly what the first facet says. And the second, he is being projected down to the first and to the third coordinate, which is exactly, again, what the other facet is telling us. So one can think about this monomial map as really every variable, it goes to the product of projections for each facet. And the kernel of this map is the ideal for the hierarchical model. And this is like this is a toric ideal, as it is the kernel of a monomial map. So in this case, one maybe using Macaulay tool can figure out that a generating set for this ideal. So in this, here I'm providing one that has 9 binomials of degree 2. And one can notice here, like if you compare any two generators, they are very similar to each other. What is changing is like some permutations on the indices. So yeah, the first one and the second one is just the changes that the very first coordinate in the indices is just from 1 it becomes 2. And we will soon, at the second point in this talk, we will make this more precise. However, before I move on, I need to say that, so associated to this map, we have this ideal, but we also have an algebra, which is the image of this map. And I am mentioning this because a lot of cases, it's very, this algebra ends up being useful because it's a monomial algebra, and the variables in the image are nicer because let's say the vectors also of the indices are shorter and so on. Okay, so let's see another example. So the independence models that I advertised earlier on. So for the independence model, this map will look as follows. So we will have the first polynomial ring from x1, 1, 1 till to x r1, r2, rm. And now each of these vertices here will induce a collection of variables. So the first vertex that has r1 like states will induce y1, 1 till to y1, r1. And similarly, the second one will induce y2, 1 till to y2, r2, and so on. The last one, ym1 till to ym, rm. And the map will send x, I1, I2, Im to the product of projections, as we said before, y1, I1, and so on. And one can notice that really, this is the Sega map. So in fact, the the independence model corresponds to the Segre embedding in algebraic geometry of m-projective planes. And so the ideal itself is just the 2x2 minors of a multidimensional matrix with entries x, I1, I2, Im. Okay, so I presented this like recipe for an ideal arriving from the hierarchical model, but why is this recipe useful? Why? And like I need to give just a justification why we call this ideal the ideal of the hierarchical model, and the answer comes from like a theorem of Diaconis and Sturmfels in '98, which they basically proved that Markov bases of hierarchical models, which Markov bases play the role of generating sets in statistics. They are in correspondence one-to-one with generating sets of this ideal that we constructed. And this correspondence is very easy. And for instance, given a generating set, reading the exponent vectors of the generators, one can get a Markov basis. So I will not tell what the Markov basis is here. However, I'll just I've given here, let's say, a detailed diagram on like how they show up in statistics. So for instance, in a hypothesis testing, so given some data and given a Markov basis for a model, one can run algorithms that produce a p-value at the end, which tells us if our data had enough information to refuse the model M. However, out of this slide, we get that really this construction is useful, and studying these ideals, it may be a good idea. Okay, so next we will introduce, as I said, like the symmetry group action and form filtrations of such models. Okay, so the first thing is recall that a hierarchical model was defined by a simplicial complex delta and a vector of states R. Fix this delta, then for any R, there is an ideal corresponding to delta and R. And consider now the collection of all such ideals. Okay, so yeah, so for every R, we have this IR, that is the kernel of the corresponding map, and we consider the family of ideals IR for R in for any possible R, and I'm denoting this with this fancy I delta. Now these ideals share a lot in common because they are sharing the main structure, but they are changing only by this vector R. However, if when R is, especially when R is large, these ideals are very, very super large, and even the computational algebra is not very useful in finding generating sets for them. And because of this is one of the motivations why we want to try to use symmetry to figure out more about generating sets of each ideal in this R. So yeah. Okay, so I did mention that we had a symmetry going on. So let's take sim R to be the product of symmetry group actions, sim R1, sim R2 times sim Rm. And we will associate to each polynomial ring RR an action by this sim R, which is as follows. Any tuple of permutations, sigma 1, sigma m, will act in a variable by acting on the indices. In particular, sigma 1 will permute I1, sigma 2 will permute I2, and so on. Sigma m will permute Im. I'll soon in the next slide give also one example, but for now let's see some like properties of this family of ideals. So first of all, this I delta, this collection of ideals is sim m infinity invariant filtrations of ideals. So what is sim m infinity? This is just the union of sim R for any possible R. And what does this mean? So I think this crowd knows even better than me what this means. But so this means that first, each of our ideals is invariant under sim R. And if you were to apply, say, sim R prime for some R prime greater than R, coordinate-wise, to IR, then you will land in the ideal IR prime. So in other words, like, all this family is super nice. You are not afraid to apply this group action because you will land still in a place you want to land on. Okay, and okay, so let's go to the stability now. So we say that a filtration I delta, this filtration I delta stabilizes up to this group action sim M infinity if there is a finite set of polynomials such that for all R's, vectors R greater than or equal to some R0 component-wise, the ideal IR can be generated by this G and permutations of this G. And the smallest such as 0 is called the vector of stabilization. Let me know if there is any questions, and I will soon give one example on this slide on what I said here. Okay, so we will use the example that I used also in the definition of the ideal. So we saw that the ideal, when R was 3 to 2, the ideal was generated by these 9 quadratics, which can be rewritten as just the ideal generated only by sim 3 times sim 3 times sim 2 of this only one binomial. So you can check that all the rest arrive by some permutation, and maybe you have more that arrive here. However, they are, because our ideal was invariant under the symmetry groups, you still land there. So you really, in this case, can present the ideal I332 by this one generator, and the rest comes from permutations. And in general, in fact, a minimal generating set for any choice of R1, R2, R3 in this case, even though it has, like, as I said, it has a large size, like it needs R1 times R2 choose 2 times R3 choose 2 generators, it can be explained or described only by this one generator up to the product of symmetry groups. And in this case, we say that the filtration itself is generated just by one generator up to the symmetry, the product of symmetry groups, and the vector of stabilizations is 1, 2, 2. Is the one that contains this one, the first one that contains this one binomial. Let me know if you have any questions. Okay. So the last slide gives kind of the motivation why one would care to talk about filtrations of these hierarchical models. Yeah, I will talk more about what it is known till now and some new results on this direction. Okay, so what is known about generating sets for these filtrations? So first thing is that if delta is decomposable, then it is known that I delta stabilizes, and the vector of all twos is a bound for the vector of stabilization, and this can easily be deduced by work of Dobra and Hosten and Sullivan in 2003. And this includes a large class of hierarchical models. However, it does not include everything. And in fact, you can find examples where our filtration does not stabilize very soon in the study. For instance, if one takes the hierarchical model, which is defined by this simplicial complex, by the boundary of a 2 simplex, so the facets are 1, 2, 1, 3, and 2, 3, then this does not stabilize. And one proof that this does not stabilize is even shown in the very first paper that I mentioned, where they what they do is they show that if you take, for instance, R3 to be 2, and you consider the filtration of ideals for any choice of R1 and R2, then you would require generators of any even degree, and this goes to infinity, and in particular, our first filtration does not stabilize either. However, if one were to say, fix this R2 to, take this R2 to be a constant, I'm taking that R2 to be, say, 2, then the corresponding filtration of ideals that arises for any choice of R1 stabilizes in this case, and it stabilizes when R1 is even 2, very, very early on. And so this kind of indicates us that maybe it's not only delta that is important for the for results in stabilization. Maybe we can get partial results by fixing some entries in the vector of states, while the rest remains, while the rest goes to infinity, varies. And for this, I will call T the vertices such that the I in M, such that Ri, I'm letting Ri vary, and while the rest, everything that is not in T, is some fixed Ci. And we take in consideration the corresponding filtration of that arrives this way. Just to be clear what T is, so in the first case, T is 1 to 3 because we're letting everything vary. In the second one is T is 1, 2, and in the third one is just 1. Okay, one main result in this direction is the following theorem that says that if T intersects each face and facet, each facet in at most one point, then the corresponding filtration, I should have written a T here, I forgot, the filtration stabilizes. In other words, what this is saying is, like, if for every facet you allow at most one of these Ri's to go to infinity, then the corresponding filtration stabilizes, and this is also called in literature as the independence set theorem. In our example here of the triangles, so the last triangle satisfies this independence set theorem because T was just equal to 1, and T intersect to each of the facets was like 1, 1, and 0. So, and we had that the last filtration did stabilize here. Another example is, so I mentioned the generalizations of the independence model. So when we have the disjoint union of simplices, then according to the theorem, we are allowed to let to infinity at most one of these Ri's for each facet. So here C2, C3, and C6 are fixed, but R1, R4, and R5, they go to infinity. They are allowed to go to infinity. And this, in fact, the generalized independence model is a decomposable model. So we already, from the other result, we know that it stabilizes when R1, R4, and R5 are equal to 2. Another example is, for instance, the fourth cycle. So if we were to let vary, according to our theorem, we can let two of these Ri's that are opposite to each other vary, while the other two must be fixed. For instance, here we are letting R1 and R3 go to infinity, and the other two, I'm taking them to be 2. Then in this case, the vector of stabilization, the corresponding filtration stabilizes when R1 and R3 are equal to 4. And here is like a part of this set, finite set G, which contains ideals of, contains binomials of degree 2 and 4. Okay, so a detailed proof for this, I have it in my dissertation. Okay, so this was about qualitative properties of these ideals. Now we will go to quantitative data. So in algebra, okay, can I take 1 second? So in algebra, one tool to get quantitative data for your ideal is the Hilbert series of that ideal. And even though everyone knows what it is, so here I have half of a slide that gives the definition of an Hilbert series. So if you have a graded polynomial ring infinitely many variables over some field K, and you have a homogeneous ideal in it, then the Hilbert series of R mod I is the formal power series in one variable whose the coefficient of t to the d is the vector dimension of this graded component of R mod I. And it is known that the Hilbert series have a rational presentation, and this rational presentation, together with containing all this infinite data in a compact form, gives us also other information, quantitative information about our ideal, such as the degree, the degree, and the dimension of the ideal. So it's useful to know the rational presentation of the Hilbert series. So in this case, this problem ended up being a difficult problem. So we decided instead to look at infinitely many ideals simultaneously and to define a similar formal power series to the Hilbert series, and which records the Hilbert series of all these ideals, and hope that this new formal power series is rational. So more precisely, so we call the equivariant Hilbert series of a filtration I delta t to be the formal power series in variables t and si for I in t, whose coefficient in front of s to the power rt, so s to the rt is like s1 to the r1 and so on. The coefficient is the Hilbert series of the corresponding of the ideal corresponding to this rt. And so so we have a new formal power series that has now more variables, so a size of t plus 1 variables, and we are hoping that that this new formal power series has a rational form. So like in a first look, this sounds that this is a more difficult problem than the problem of finding the Hilbert series of each ideal itself, because we are summing over things that we think we don't know the rational presentations of. However, the first example that I'll introduce here tells that there is hope, and this problem may be this may be a good way of finding the Hilbert series. Okay, so so the hopeful example is the independence model itself. So in this case, even though the rational form of the Hilbert series is difficult when m is greater than 2, the equivariant Hilbert series it has this very nice simple formula. So summing over all of them times s1 to the r1 and so on, sm to the rm, gives you this very nice simple formula. And this is also the equivariant Hilbert series of the Sega product of the infinite dimensional planes by the correspondence that I mentioned before. Okay, so before we think that all things really become easier, let's look at one example that sets us more down to earth. So the example is the example of let's take the full simplex that is just a one simplex. So you have an edge here, you have and each of these two vertices have R1 and R2 states, and R1 and R2 are going to infinity. The kernel of the map, in fact, here is if you start with a simplex, the kernel of the map is just 0, which means that the quotient ring is just all the polynomial ring itself here. And however, the equivariant Hilbert series would be the sum over every R1 and R2, for every R1 and R2 of the Hilbert series of this polynomial ring, which is just 1 over 1 minus t in power R1 times R2, because this is the number of variables there, times S1 to the R1 times S to the R2. And to my knowledge, this is, I have personally worked a lot in this naive problem. and I have not been able to figure out if this is rational or not. I would love if someone else would have an easier way to, or would at least give me a definite answer on this. But however, this seems like yeah, at the beginning a naive problem, but rational, there is no rational presentation. However, I do not have a proof. I just can say now that this is, to my experience, a difficult problem. However, if we were to make a small change to our filtration, so if we were to choose R2 to be equal to some constant C, then our model would look like this. Then in this case, our equivalent Hilbert series, which is like, again, the same thing as before, is 1/1. So is the sum of the Hilbert series of the same polynomial ring, but now I have C times R1 variables times S1 to the R1. You can do just very simple manipulations, and you get a rational form. So making this small change, like fixing one of these number of states, you do end up having a rational equivalent Hilbert series. And because of this, so the suspicion is that also the rationality of this equivalent may depend on delta and on this vector of states. And so this is like the main result that we have in this direction. So the equivalent Hilbert series for the filtration is rational if either the size of T is 1 or any of these two facets are disjoints and each facet intersects T in at most one point. So the second condition here is exactly the independence set condition, and the first one is the generalized independence model condition. So this is like one of the examples that are covered by this theorem. So we are letting R1, R4, and R5 go to infinity, while C2, C3, and C6 are some constants. So in this case, we say that the corresponding equivalent Hilbert series is rational. And we also give ways how to compute this rational representation. Before I go to, so I'll give a very brief sketch of the proof. But before I go there, I will say what is the inspiration for the conditions and for the tools in the proof. So the conditions, like as it was mentioned already. So we had here the independence set theorem that came from this paper of Hilbert and Sullivan, and we use regular languages to prove the rationality, which was first done by Krondiking and Snowden in proving the rationality of some other Hilbert series. Let me know if you have any questions. Okay. So I mentioned that, yes, we use regular languages. And in order to give a sketch of the proof, I will need to give a fast food introduction of regular languages. So take sigma to be an alphabet. So I'm taking here the alphabet with just letters A and B, and take sigma star to be the free monoid on these letters. So it's like epsilon, where epsilon is like the empty word, and A, B, and so on. And any subset of this sigma star is a language. However, regular languages are subsets of sigma star that are recognized by finite automata. So what are finite automata? A finite automaton is a simple machine that inputs words and inputs letters and outputs words that satisfy certain rules. So I'll explain the rules via this simple example. So first, a finite automaton must have a finite number of states. So our machine here has 3 states, which are indicated by these circles. And it must have transitions between states, which are indicated by directed edges. And these transitions are labeled by letters. So we have transition from 1 to 2 with A, and from 2 to 3 with B, and from 3 to 3 with B. And it must have a starting state where you start like reading your word, and it must have at least one. So in this case, the starting state is 1, and it must have at least one accepting state, which I am indicating it with a double circle. So 3 here is an accepting state, where state when I can read the output. And the way how we get the output is we start at the starting state and we do what the arrows tell us. So here, the only option I have is to just move with with A and go at state 2. And when I'm at 2, because this is not an accepting state, I have to move out of 2, and the only option is via this B. And when I go at 3, then I am allowed to read what I have already produced. So I have produced A, B, so I can read A, B, or I can read another B and another B because I have a loop here and I can get that, read that, and that is an accepted output. So in fact, the output of this simple finite automaton is like all the words of the form A times B to the n. So A, B, 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 B. So we can give weights to letters and we can extend these weights multiplicatively to words. So for instance, here I'm giving weight T to A and weight in like the previous slide with the equivalent Hilbert series. Okay, so we
Aida, you froze for a minute, at least for me.
Okay. For a minute, what does it mean, a minute?
Like 10 seconds.
Okay.
I don't know if that happened to anyone else or not.
Maybe it did.
Okay.
Okay, so sorry. So, okay, I don't know where to start exactly now, but.
It was when you were describing the weights.
Okay, so we have this language here, A, B to the n. That is the output of our automaton. And I was saying that we can give weights to letters and we can expand these weights to words multiplicatively. So if for instance, I can give here to letter A, I can give weight T, and to letter B, I can give weight S. And then any word A, B to the n will have weight T times S to the n. Now, any language and the weight function on it defines a formal power series in the following way. So, okay. So I will denote this formal power series with P of L rho, and will be the sum over the weights of words for every word in the language. So in this case, will be the sum of weights of A, B to the n for every n, which just a simple, this is a very simple calculus problem. This is T times, like geometric sum, T times S, 1 minus S. And in fact, why we did all this? We did all this because this last formal power series is rational whenever you start with a regular language. And this is also all like the kernel of our proof. So in our proof, we want to prove that the equivalent Hilbert series are. So what we do is we show that there are out there some regular languages and weight functions whose formal power series equals to our equivalent Hilbert. And the last theorem here does the job. Okay, so I'm giving another example that is now more for our problem. So if I take this other finite automaton, and so I claim that the output of this one are all the words in this like one plus tau 2 plus, this just means that I have to read at least one tau 1, and then I have to follow it by reading at least one tau 2. Where also the other condition is that tau 1 and tau 2 appear next to each other only in this order. So I don't have tau 2, tau 1. So that's all what this is what this finite automaton does. And similarly, I give weights now to zeta. I give weight T, to tau 1, I give weight S1, and to tau 2, I give weight S2. Then the formal power series in this case, I forgot this should be a T here. instead of 1 is S1, S2 over 1 minus S1, 1 minus S2 minus T, which is exactly like a formula that we saw before for the independence model of two random variables. Okay, yeah. So if somebody has a question on these dots, this is not a miracle. If you have the finite automaton, then the job is done. It's very simple to find the rational representation, and this is like, these are standard things in the literature of regular languages and finite automata. Okay, so and here I'm just giving just one a little bit a different interpretation of the main proof from what it is already written there. And this is because I want to say that the proof that we have in the paper does give place for applications to other problems. So the recall that like all what these two conditions were that you have a disjoint union of simplices where at most one of these Ri's went to infinity for each simplex. So the sketch of the proof, I said the idea is that we create these regular languages, but first, in order to prove some bijection between the two worlds, we turn our problem to the filtration of algebras, and this is because we work now with monomial algebras, which ended up being easier. And for every facet, one can think of that proof as in the following way. For every facet in the facets of delta, one can determine a language and a weight function whose formal power series equals to the equivariant Hilbert series of the model restricted to that facet. And then we take all these languages and these weight functions, and we form a new, we manipulate them in a certain way, and we form what we call a tensor. What we will call, we have not called them that way in the paper, what we will soon call tensor language, sorry, a Segre language and the Segre weight function. And these new manipulated languages have the desired property that their formal power series is equal to our equivariant Hilbert series of the initial problem. For details on like the bijection between the two worlds, I welcome you to read the paper. Okay, but as I said, like I took time to add this part 2 just to say that this idea can be expanded outside of the hierarchical models, outside of this very specific problem, and yes, and that's what and more meant here. So with a very similar idea to that, we can define, we can give answers for Segre products of monomial algebras in general. So if we take, say, a monomial algebra A in K of Y, what K of Y means like is an infinite dimensional polynomial ring with variables Y indexed. And B also another monomial algebra, but in another infinite polynomial ring, but whose variables are very different from the first one. Then we take the Segre product of two algebras, which is defined the following way. So each algebra in this Segre product is of the form AN Segre BM for any NM and M. Where, yeah, this Segre product is is just generated by products of generators for each of the two algebras. And then, I'm not talking here about filtrations with respect to anything. This is a very like very general construction. And the idea is that if one has languages that correspond to, and weight functions that correspond to these filtrations, and they have that nice property that we mentioned earlier, then we can form new regular languages and new weight functions out of them that behave very well with respect to this to the Segre filtration. Okay, and so this here is saying. So if the filtration formal power series of them is equal to the equivariant Hilbert series of the algebra. I hope some. Can you hear me?
You froze for just a second, but I think it's okay.
Okay. Okay, so if we have like a language and a weight function for this monomial algebra and another language and weight function for the other monomial algebra, such that their formal power series equal to our equivariant Hilbert series, then the two languages can define with them we can define a Segre language and a Segre weight function, such that the formal power series of the new language is equal to the equivariant Hilbert series of the Segre product. Currently, we have been applying this theorem also to other filtrations of algebras that are not finitely generated up to the symmetry group action, but still they are finitely generated with respect to some shift operator. Okay, so what did I say? Okay, so yeah, so as a result, algebra is used in analyzing hierarchical models. Sometimes it's best to analyze infinitely many such models simultaneously. Equivariant Hilbert series record quantitative data for infinitely many ideals, and we showed their rationality via some regular languages, and at the end we mentioned the Segre languages and weight functions in a more general setting. And I usually prefer to end my talks with some open questions that you may have had, but I am spoiling them. So one question is like, does finitely generated up to, I'm writing it very vaguely, but I could have rephrased it in the language that I mentioned here, but does finitely generated up to a given action means a rational equivariant Hilbert series? And so this is motivated because in the case when we are working over the polynomial ring with variables x, c times n, this is true. However, when you leave that, it's very unknown. And one other question is like, we talked about this finite automata. Can anyone do the number of states in the minimal automata means anything, or the transition? So can we get any additional information from the structure of the language and the finite automaton? And lastly, so I talked about these monomial algebras, and associated to them there is a lot of polyhedral geometry, and lately Kalle and Romer have been studying these monomial algebras, have started to study them. However, associated to them there are polytopes and there are error series. So what about like an analog to this equivariant Hilbert series? What about equivariant error theorem? And this is yeah, so these are some references, and this is all what I've prepared. Thank you.
Okay, let's thank Aida. And are there questions?
I have a quick question. So I'm not sure I understood that properly, but when you're doing the equivariant Hilbert series, you had representations of certain symmetric groups, right? And you recorded their dimensions, if I understood correctly. So what would you get if you recorded the symmetric function instead? Like, you know, in a bunch of variables.
Can recorded the symmetric function? You mean
the character of that symmetric group instead of just the dimension?
I don't understand so when you say I recorded the dimension, what does that mean? Sorry.
I mean, so like your Hilbert series was looking at the dimensions of things, right?
It's looking at what is the Hilbert series recording, you are saying?
Yeah, so the equivariant Hilbert series, I guess maybe I didn't really understand what the equivariant part of it was.
Oh, the word equivariant is because I'm studying these filtrations, and they are related to like they are a filtration with respect to the product of group actions.
Okay.
So,
So if I didn't just look at the dimension of each graded.
yeah.
If I looked at the character of the symmetric group acting on that graded piece, if all of those would be also rational or interesting.
Yeah, I don't know. Like that's all what I can say. But I can talk to you later on at 3 before the seminar.
I myself thought about that in like the case of
Okay.
algebras generated in degree 1, and I wasn't able to figure anything out. But I think it's a good question.
Okay, thank you.
Yeah, I actually had 2 questions. So one, you said in one of your main theorems, you said that it was algorithmic. Like,
Yes.
Does that mean like you have an algorithm that sort of takes in a simplicial complex and spits out the automata?
The algorithm is you input this, yes, you input the structure, you input these numbers, C1, like C2, C3, and C6, like the fixed ones. And in fact, it does not spit the automaton. Like I have already done that. Like I have in the proof, I have already reduced it to the minimal automaton. So it's like the best possible automaton you can get. And I have done the algebra. And so the algebra is written. And so the output is exactly like, it's just some linear algebra because I already had it, I had constructed the finite automaton, even though it is like, okay, I'm doing that, but I'm really like, I did all the job till to the finite automaton. So the algorithm does only linear algebra because the finite automata was done in the automaton was done in the proof. And yeah, it spits just the rational presentation. And it is, I think it is optimal, except the part where I'm not very good at the computations, you know, like somebody can write the code better. However, like the method, I think is very optimal. It cannot get better itself. Like,
okay.
And also, yeah, since we're here, I can say also this. We also give another way of computing using roots of unities for this C2, C3, C6, but it's not as the finite automata algorithm is better.
The other question I had was, so in the work that Uwe Nagel and Tim Romer did previously, they did equivalent Hilbert series, and that was in like the case where things were generated in degree 1, where you just had like one infinite set of variables, basically.
Yes, one.
Yeah. And like the algebras you're treating here kind of don't fall into that case, but they're kind of special. They're special algebras. And so I was wondering if like you had any sense of like what other generalizations of that previous one might exist. Like if you worked with algebras generated in degree 2, but maybe not of this exact form, if you had thought about any of those, and if you get rational series there.
Okay, well, I have one question to your question.
Yeah.
So I don't answer another 2 question that was not asked. So you said, when you said algebras, you mean, okay, do you mean about the work of Uwe and team in 2015? Like the first one?
Yeah.
They work with ideals that live in polynomial rings of the form x c times m.
Yeah. So they treat like arbitrary ideals in those kinds of rings.
Yes.
And you're working with either subrings or ideals in things where you maybe have 2 or 3 indices going to infinity, but they're of a very special kind.
Yes. Okay. I see.
So I was wondering, if there's more general kinds in this broader sense that you might think might be rational still.
Yeah. So there are classes where I suspect things go well, but I don't have proof, so I feel like I'm not allowed to say they're good. But what I got from this, for instance, from this work is like let me go here. 1 second. Let me go here. So that kind of work or that kind of result appeared here in a different form, but appeared in the images. So the images here, the variables in the image live in those type of polynomial rings of the form x c times n. So in general, if one is able to write theoretically the image as being in those polynomial rings, then they should be able to prove that it's that you have rationality. So in other words, I suspect that the first condition here is not needed. The only condition that is needed is the independent set theorem, which is basically that the algebras of my ideals, or in general the image, should live in a polynomial ring of the form that Uwe and team had.
Right. Okay.
That's my strong belief.
Okay, thanks. Are there more questions? All right, well, let's thank Aida again, and I will stop recording now and